talking about local energy dissipation for continuous incompressible Euler flows. So the main problem I'll be talking about is called the strong Onsager conjecture, and this conjecture arises from turbulence somehow. So I'll explain the importance of local energy dissipation in turbulence. And the strong Onsager's conjecture is when you take Onsager's conjecture and include local energy dissipation. So after our survey results, I'll give some of the highlights of the first construction of continuous Euler flows that exhibit local energy dissipation. So let's start with, here are the Euler equations. I've written them in divergence form with the summation convention for repeated index J. And they are derived from conservation laws. The equation 3 represents the conservation of momentum for any given region omega, and equation 4 represents the conservation of mass for any given region omega. And if you have solutions that are continuously differentiable, 1 and 2 are equivalent to the integral forms 3 and 4, but the integral forms make sense when your velocity and pressure are just continuous functions and provide a notion of weak solution to the equations. So weak solutions necessarily conserve momentum, that's built into the definition, but they may not a priori conserve energy. When you have smooth solutions to the Euler equations, you can take the dot product with V and you derive something called the local conservation of energy. And when you integrate in space, this implies the conservation of total kinetic energy, that the integral of V squared remains constant in time. But this computation involves things like the product rule that require regularity to justify, and a natural question is how much regularity must be assumed to guarantee the conservation of energy. So in 1949, the physicist Lars Onsager made a conjecture about what is the threshold regularity for energy conservation, and his conjecture is the following: that if you have a Hilbert continuous solution, a solution in C alpha for alpha greater than 1/3, then the solution has to conserve energy. But for alpha less than or equal to 1/3, there exist solutions that fail to conserve energy. So Hilbert 1/3 is the conjectured threshold for energy conservation for the Euler equations. Why was the physicist Lars Onsager interested in this? Well, his interest came from studying dissipation of energy in turbulence, which I now want to describe. So to turn to the study of turbulence, we talk about the Kolmogorov's 1941 theory, which involves the 3D Navier-Stokes equations, which have this viscosity term on the right-hand side that models internal friction. And we're interested in the regime where viscosity is very small compared to characteristic lengths and velocities of the fluid, because that's where turbulence occurs. Now, you might think that when viscosity is going away, going to zero, that energy dissipation would cease to happen. When viscosity is positive, energy dissipates, but if viscosity is going to zero, you might think that goes away. The starting point of the K41 theory is also called the zeroth law of turbulence, is the opposite of this occurs. There is energy dissipation that is strictly positive as viscosity goes to zero. Moreover, the energy dissipation rate, together with the viscosity, can govern all the statistics of turbulent flows in this theory. For example, if you want to know the size of velocity fluctuations, this theory will tell you that difference in velocity scales like distance to the 1/3 in the relevant range of length scales. And this 1/3 arises because it's the only power law consistent with dimensional analysis that you can form with the dissipation rate. So Onsager was interested in how this dissipation of energy that's independent of viscosity could happen, and he considered even the limiting case where viscosity equals zero. So he explained the dissipation as follows. You could consider solutions to the Euler equations in Fourier series form. So you write down the Fourier series for your solution, and you write down the Euler equations in Fourier series form. And what you notice is that low wave numbers interact with high wave numbers. So the energy that starts out at low wave numbers can move to higher wave numbers by these nonlinear interactions. And this cascade can happen so fast that the energy reaches infinite wave number in a finite amount of time. So this gives you a mechanism for dissipation that can happen even with no viscosity at all. So there's no viscosity in this equation. So he observed that only low regularity solutions to Euler's could exhibit this dissipation. And he stated that if you have a solution in C alpha with alpha greater than 1/3, this must conserve energy. On the other hand, the turbulent solutions are supposed to have regularity exactly equal to 1/3. and dissipate this energy. So the amount of energy at frequency lambda would scale like lambda to the minus 2/3. So this brings us to Onsager's conjecture that you have solution that for alpha greater than 1/3, solutions conserve energy, and for alpha less than or equal to 1/3, the continuous solutions may fail to conserve energy. How much do we know about this conjecture? Well, the conservation of energy above 1/3 seems to be well understood by Eink and Konstantin and Titi, and refinements by other authors that show that you can even improve conservation in this Besov space with 1/3 regularity, but not in C1/3. The proof of energy conservation doesn't go through, and you may have dissipative solutions that have C1/3 regularity. So then the next step is, with this seems to give a clear picture of energy conservation above 1/3, and you want to show that below 1/3, there are solutions that fail to conserve energy. And moreover, these solutions should arise in the zero viscosity limit of Navier-Stokes. Let's talk about the zero viscosity limit of Kolmogorov's theory for a second. If you take the zero viscosity limit, then this distance to the 1/3 scaling holds for all length scales, which actually gives you some strong compactness. So you get strong convergence along subsequences to Euler flows. The viscosity goes to 0. Euler flows that dissipate kinetic energy and have Hilder regularity 1/3. So that's what formally is the limit of the K41 theory. And so let's state this more mathematically as a conjecture. Is there a sequence of smooth, weak solutions to Navier-Stokes with the following properties as viscosity goes to 0? The C1/3 norms remain uniformly bounded according to the scaling law, and they exhibit the 0th law of turbulence, that energy dissipation is independent of viscosity. So they should dissipate energy independent of viscosity. Now, when you think about this conjecture, you should realize that we're not talking about fixed initial data. The initial data are not fixed. The solutions and the initial data are smooth, but they're becoming increasingly singular as viscosity goes to 0. They're approaching a solution that is Hilder 1/3 that dissipates kinetic energy. So when we now want to take the zero viscosity limit, but the limits are not only going to dissipate kinetic energy, they're going to dissipate kinetic energy locally, because they inherit local dissipation from the Navier-Stokes equations. So this is the local energy equality for the Navier-Stokes equations, and the right-hand side is non-positive. And when you take a limit of this local energy equality, you get something called the local energy inequality, which summarizes that energy should be dissipated locally for any strong limit of the Navier-Stokes equations in L3 of classical solutions. So any physically relevant Euler flow has to satisfy this local energy inequality, and that brings us to the strong Onsager conjecture that there are C1/3 solutions that satisfy the local energy inequality and dissipate energy. These are supposed to be zero limits of Navier-Stokes solutions, and this conjecture follows from the K41 conjecture I just discussed by the Aubin-Lyon-Simon lemma using this scaling law. So notice that notice that the solutions to Euler here may not be unique, and there's a physical interpretation for this non-uniqueness. When viscosity is positive, the Navier-Stokes solutions should be smooth and unique. However, the time scale that turbulence remains predictable shrinks to 0 at high Reynolds number, and as a consequence, the limiting Euler flows may be non-unique. Here, the solutions are C1/3. The uniqueness, proof of uniqueness requires C1. But on the other hand, before we ask about non-uniqueness, we should ask about existence. Are there even incompressible Euler flows that fail to conserve energy? And the first examples were shown in breakthrough works of Scheffer and Schnirelmann, and a more systematic approach to constructing these examples was given by Delelis and Sekelichidi using the method of convex integration, where they constructed examples in L infinity with local dissipation. Now, this doesn't quite give a result towards Onsager's conjecture, because these solutions are nowhere continuous, and there's an obstruction to making continuous solutions with this method. But later, Delelis and Sekelichidi were able to overcome this obstruction and gave the first result towards Onsager's conjecture: C alpha solutions with alpha less than 1/10 that failed to conserve kinetic energy. So this result towards Onsager's conjecture was improved by myself and also by Buckmaster, Deleuze, and Sekeli-Hidi. In 2016, I solved the full conjecture by showing compactly supported solutions for alpha less than 1/3, and Buckmaster, Deleuze, Sekeli-Hidi, and Bucol showed furthermore that you can prescribe the kinetic energy. So the total kinetic energy can be increasing or decreasing as a function of time. It turns out the method is not capable of getting the endpoint results, but I was able to get results where asymptotically at small length scales you approach the endpoint as distance goes to 0. So what this array of results tells you is that we understand energy dissipation below 1/3 very well, the dissipation of total kinetic energy. What that tells you about turbulence is that these energy cascades that Onsager was predicting can really happen, and they're consistent with the scaling laws of turbulence. But the unfortunate thing about them is that the solutions are not physically admissible. They cannot arise as zero viscosity limits because they do not satisfy the local energy inequality. So for the strong Onsager conjecture, we want physically admissible solutions that satisfy the local energy inequality. What do we know about in this direction? Well, we know there are bounded measurable solutions that satisfy the local energy inequality. This is due to Deleuze and Sekeli-Hidi, but their solutions are nowhere continuous. And also they exhibit a great amount of non-uniqueness in the sense of a bare category result producing non-uniqueness. But they're nowhere continuous, and there's an obstruction to getting continuous solutions by this method. And the result I want to discuss today is the first result on the strong Onsager conjecture, which produces continuous solutions and shows for alpha less than 1/15, there exist solutions that dissipate energy and satisfy the local energy inequality. And moreover, there's a lot of non-uniqueness for these solutions that you can produce an infinite family with the same initial datum and the same dissipation measure. You might think that the dissipation non-uniqueness is due to information lost in the zero viscosity limit, and that the dissipation measure would allow you to recover this information. But no, even if you fix the dissipation measure, the solutions are non-unique. And furthermore, the dissipation measure could be 0, so you could impose energy conservation locally, and you still have non-uniqueness. And the non-uniqueness is family with positive Hausdorff dimension. This is proved by some kind of probabilistic argument. Okay, so this is the existence of the solutions is what I want to discuss today. And but I must mention that this result has been improved recently by Deleuze and Quan, who improved the result to alpha less than 1/7 for solutions that locally dissipate energy. All right, and the idea here is using the Mikado flows of Daneri and Sekeli-Hidi and discretizing them the right way to get this result. So it's great, very nice new paper. And so I want to talk about the existence for alpha less than 1/15, the first result, and what are the ideas that make this happen. So I'll talk about first of all, what is the general idea of convex integration that is used to construct these solutions, and then start talking about the ideas for local energy dissipation. For convex integration, I'll give you a tour of how it works in general, and then show you what ideas you have to add in to get solutions that locally dissipate energy. A highlight of the local dissipation will be that there's an arrow of time in the construction that is important. This is a new feature of convex integration arguments, and also a new feature of convex integration arguments is that the proof relies on trilinear energy cascades. These play a leading role in the proof. So let's begin talking about constructing Euler flows. The way we do it is we approximate them by solutions to the Euler Reynolds equations. So here we relax the Euler equations to have a forcing term, which is the divergence of the symmetric tensor R that measures the error in solving the Euler equations. So when the error tensor R is 0, you get a solution to Euler. And it's easy to show that every continuous incompressible Euler flow is a limit of a sequence of Euler Reynolds flows, with R tending to 0. So what we want to do is approximate our Euler flows by constructing a sequence of Euler Reynolds flows, indexed by Q. And the way we construct this sequence is we start with lower frequency BQ, and we add in a high frequency correction, capital BQ, and a correction to the pressure, capital PQ. And the goal of these corrections is we're going to cancel out the error RQ, and we get a new error RQ plus 1 that is way smaller than RQ. So we add these corrections, cancel out the error gets smaller, and we repeat this process over and over. When we repeat this process, the error goes to 0 rapidly, and the corrections we add also get rapidly smaller too. So in the end, we get a uniformly convergent series that we can sum to get continuous solutions because the error is tending to 0. So that means that we can now focus on just one step of the iteration where we have a single Euler Reynolds flow R, and we're adding a single correction, capital V, and a correction, capital P, to the pressure, and these are designed to cancel out the R. And after we cancel out the R, we should be left with a smaller R that we'll call R star, and this R star should be much smaller than the previous error R. So we add corrections to the velocity, add correction to the pressure, cancel out the old R, and get a new R star that is way smaller. This sounds very general, but when you try it, you run into these difficulties that the error terms you see they're supposed to be the divergence of a small tensor, but are either not in divergence form or the divergence of a symmetric tensor that is not even small. So an important part of the proof is that we have to solve a divergence equation. It's only to get our new error. It's only after we solve this divergence equation that our new error is small, and we have to design the velocity correction and the pressure correction very carefully to cancel out the R in order to ensure this new error is small. Okay, so that's the idea. We use a high frequency correction. And how small should the error be? Well, I want the high frequency correction to oscillate at frequency lambda, and I want the new error to be of size 1 over lambda, ideally. And so when we actually add a correction, we get two types of error terms. We get linear error terms, and we get nonlinear error terms. And all of these should be of size 1 over lambda, ideally. And there's also another type of error term that has to do with regularizing the velocity field and stress, but we'll ignore this error term. So let's talk about what kind of wave. It should be a high frequency divergence free wave that we're adding. And we follow my proof, an approach by myself and Nicole in 2013, where we have a frequency lambda plane wave and an amplitude that we can choose. And these have the following properties. The wave is divergence free by choosing the small correction here, right? Appropriately. The wave should be transported by the coarse scale flow. So the phase function solve a transport equation, and the phase gradient is orthogonal to the amplitude. So other than this condition of orthogonality, we get to pick the amplitude however we want, and we get to pick the phase function however we want. And furthermore, it should be localized in frequency. So we use a Luray projection that's localized in frequency to form this wave. To use such a Luray projection, we use something called the microlocal lemma, which tells you what happens when you have a frequency lambda wave and put it into a convolution operator, and says to leading order you get a multiplication error operator with a very explicit form of the error. So I'll skip the proof of that. So we have this frequency lambda wave with an amplitude we get to pick and a phase function that is transported by the wave, and it's divergence free. And now we throw it in, and we want all the error terms to be of size 1 over lambda. So let's try seeing the linear error terms, how those work. The linear error term, you see the advective derivative of appearing. That's the derivative along the trajectories, and it has an important role here. So what you're afraid of is you're afraid of differentiating the phase function because of that large frequency lambda. But what saves you is the fact that the phase function is transported along the flow. So this advective derivative does not hit the phase function, it only hits your low frequency amplitude. That leaves you with something nice and low frequency times something high frequency. So the right-hand side is isolated to frequency lambda. And when we solve the divergence equation, we get a solution that is also isolated to frequency lambda that has size 1 over lambda. 1 over lambda because you solved the first order elliptic equation. So that's how you handle the linear error terms. They're high frequency. But then for the nonlinear error terms, we have low frequency contributions. And what we want is for the low frequency part of the nonlinearity to cancel out the low frequency part of the error. So when you expand your wave into individual plane waves, the low frequency part is when you have one wave multiplied by the conjugate wave. In that case, you have e to the I lambda c multiplied by e to the minus I lambda c. So the phase functions cancel out here, and you're just left with the sum of the squares of the amplitudes. Now remember, we get to pick the amplitudes pointwise, so this here can be whatever tensor, whatever symmetric tensor that's positive definite that we want. And if we use the pressure, we can also get negative definite tensors. So no matter what the low frequency part of the error is, combining the amplitude and the pressure, we can cancel it out. To get the amplitude, it's like taking a square root of the error term. And then we cancel out, and this error term becomes 0 at every single point. So that's how we get rid of the low frequency part of the error. What we're left with is the high frequency part of the error. And the high frequency part has this dangerous term where you differentiate the phase functions and you pull down this large frequency of parameter lambda. So how do we handle this? Well, there's a dot product here where your amplitude is dotted with the phase function. The amplitude is already orthogonal to its own phase function, but it may not be orthogonal to the other phase function of the wave it's interacting with. So what we want to do is we want to impose that all the amplitudes are orthogonal to all the other phase functions. So we impose that all the phase functions align with each other, that they basically point in the same, phase gradients are all in the same direction. That way all the amplitudes can be orthogonal to all the phase gradients. The price we pay is that means we are only getting rid of one component of the error because our amplitudes are restricted to a hyperplane. So we get rid of one component of the error, and there are still two more components that we have to get rid of that are orthogonal to the second and third standard basis vectors. And so in each stage, we get rid of one component, and then the second stage, we get rid of the second, the third stage, we get rid of the third component. But then after the third stage, we've actually gotten the error to become smaller. So within 3 steps, we make the error smaller, and then we repeat this whole process over and over. The error becomes smaller by iterating 3 steps at a time. All right, so that's how we get the error to be smaller and how we get solutions that don't fail to conserve energy. And now we need some additional ideas to get these solutions to locally dissipate energy, to satisfy the local energy inequality. So what else goes here? So the idea for getting Euler flows was to relax the Euler equations. So the idea to get local energy dissipation is to relax the local energy inequality. You want this approximate dissipation on the left-hand side to be bounded by some term, error term f, and you want f to go to 0. You want to somehow have a scheme where your error r and your error f simultaneously go to 0. So this is the basic idea, although it's not actually going to work the way I've written it here. But I just want to, at this present time, I want to note that we've defined this approximate dissipation, and notice that it's cubic, and that'll be important for later on. So, but this is the basic idea. You want to relax the local energy inequality, but you need to relax it in the right way in order to get the scheme to work. And the right relaxation is a canonical one, which is the following. Is the definition of a dissipative Euler Reynolds flow, and involves not only 1 but 3 error terms that are called kappa, r, and phi. R is the same stress, and it's interacting with the velocity field here on the right-hand side. The kappa and phi are the unresolved density and the unresolved current, and they're the new error terms. And our idea will be that we want to have a scheme where we cancel out the kappa, cancel out r, and cancel out phi, all three of them simultaneously. And as kappa, r, and phi go to 0, you end up with a solution that satisfies, with 0 on the right-hand side, that satisfies the local energy inequality. So this is the relaxation of the local energy inequality. Now we want to do an iteration where in each stage of the iteration, we add a correction, capital V, and correction to the pressure. And our corrections will produce a new approximate dissipation with a new kappa, a new r, and a new phi that are all way smaller than the previous error terms. And this is what we iterate over and over again. So we're going to have to combine our previous scheme that I described with the way of getting rid of the kappa and getting rid of phi, and getting rid of, furthermore, all of the error terms that arise. So there are many because the approximate dissipation is cubic. So you end up with linear terms, such as the first one, quadratic terms that are low frequency, such as the second one, quadratic terms that are high frequency, more quadratic terms, and cubic terms, trilinear terms. So these are all the kinds of error terms, and then there are some more error terms that I haven't written. So much more error terms than usual. And so how do we treat these error terms? Let's look at the linear error terms. We have these linear error terms, and the first step will be to regularize the velocity field. We replace V with V epsilon. And when we replace V with V epsilon, the error can be absorbed into the new kappa and the new phi. Notice that this term is an advective derivative, and that gets absorbed into the new kappa. And the other term is the divergence that gets absorbed into the new phi. So we have the right structure for the new error terms. And now what we're left with, we have something low frequency, and the capital V is our high frequency guy. And we end up with interactions of stuff that's high frequency with stuff that's low frequency. And we recognize what these are. The first term is the divergence of the transport term that I showed you before, and the second term is a regularized version of the left-hand side of Euler Reynolds. So we plug in the divergence of the transport equation and the Euler Reynolds equations, and what we get, we have something that almost has the right form. This divergence, we just want to put it on the outside so that we get a term that has divergence of V contracted with R, which is the one part of the form that we want. And then the remaining terms has frequency lambda because it's a term with high frequency lambda multiplied by stuff with low frequency. And this is something, because it has high frequency, we can solve the divergence equation and absorb it into the new current phi. So that becomes part of the new current. So I call this digging to find the right structure in the error terms, and this is one example. And now the other examples I want to show you are how to cancel out the new error terms, canceling out the new density kappa and canceling out the phi. And so let's start with how we cancel out the unresolved flux current. What the new feature here is we have trilinear cascades. So a certain group of our waves are going to have a low frequency cascade, trilinear cascade that's going to cancel out the current phi. So we pick waves, just special trios of waves where all the phase functions cancel out and you get something low frequency. After you get something low frequency, you can use it to cancel out the current. So trilinear waves that are being transported along the flow are interacting to cancel out the current. This picture is exactly like something called the Lagrangian direct interaction approximation theory of Kreiknen, which Kreiknen proposed to model turbulent energy cascades. So here it's really happening. We have real examples that are constructed with such trilinear cascades of waves transported along the flow. So that's what the low frequency interactions do, is they cancel out the phi for these special trios. And then the remaining trios are high frequency. And somehow those high frequency waves have the right structure to satisfy good estimates after you solve the divergence equation. Now, so we've used trilinear cascades to cancel out phi. What about canceling out kappa? Well, we similarly want to isolate the, we use the amplitude of v squared to cancel out kappa. That we split this up into low frequency and high frequency terms. The low frequency terms are when the wave interacts with its conjugate wave, and we want that to cancel out kappa. Now, we know that this can't exactly happen because the wave times its conjugate wave is going to be something positive definite. And we know that we can't cancel, we don't know that kappa is negative. So we have something positive that's trying to cancel out something negative. But what we can do is we can use a degree of freedom, which is that we can add and subtract a function, e of t, and then the positive term here can cancel out the term kappa epsilon minus e of t, which will now be negative. The stipulation is that this term we added and subtracted has to be decreasing or non-increasing. And this is where the arrow of time in the construction comes in. So as long as it's non-increasing, we can take this term and throw it into the relaxation of the energy inequality. Then we can use the amplitudes to cancel out kappa epsilon. There is a catch, however, which is that we can't quite cancel out kappa epsilon just using this equation because there's a linear dependence with another equation that we're trying to solve. Namely, it's exactly half the trace of the term that appears when you're trying to cancel out the stress. So you need to cancel out the stress R and the current density kappa simultaneously. So how do you do this? To make these two equations compatible with each other, there's one degree of freedom we have, which is choosing the pressure. So there is a unique choice of pressure, which will make these two equations compatible with each other so that when we cancel out the stress, we will simultaneously cancel out kappa epsilon. And that'll cancel out R epsilon and kappa epsilon at the same time. So that's using a degree of freedom, which is to choose the pressure. Now that's one conflict, but there's another conflict in this game, which is that we have to cancel out the current phi and the stress tensor R simultaneously, and the current and the density kappa. So what we've done is we've used trilinear cascades to cancel out phi, but we also, those same waves appear when we are trying to cancel out the error tensor R. So somehow we have to make sure that these two things can happen simultaneously. So the way we do that is we take the waves that are used to cancel out phi from these special trilinear cascades, and we remove them from the sum and put them on the right-hand side of the equation. So here they go on the right-hand side of the equation. So now we want to use the remaining waves to cancel to the remaining waves do not depend on phi. Only these special waves here depend on phi. The remaining waves will be used. We take basically a square root of the equation to find the amplitudes for remaining waves. So somehow the remaining waves will depend on the ones that are used to cancel out phi in this nonlinear way. So this is a good idea as long as these waves that are used to cancel out phi are lower order terms. But demanding that, so we're somehow canceling out the current through trilinear cascades, but then the trilinear cascades are absorbed in quadratic cascades into the other waves that compose the solution. Now this is an okay idea as long as the waves used to cancel out the current are lower order, but that poses a problem because that threatens the whole solution, the iteration, requiring that phi be lower order in size. In particular, when you look at the new current, you need to show that the new current is lower order in size, and you see dangerous terms where the velocity interacts with the pressure, for example. This is one dangerous term that appears. And what you notice is that this term, where the velocity interacts with the pressure, is actually too large. It does not have the right size to be absorbed as a lower order term, and it makes you think that we're not going to be able to succeed at all. But something miraculous happens that saves the whole proof, which is the following, that even though this interaction with the velocity and the pressure is too large, the divergence exhibits a special cancellation. When you take the divergence hits the phase function, and you get this contraction where the dot product, where the phase gradient and the amplitude are dotted with what's left of the identity tensor that is part of the pressure. And this term, that's the leading order term, is 0. Or approximately 0, because of the geometric arrangement of how we've chosen our amplitudes and how we've chosen our phase gradients. So this term actually just cancels out. The divergence of the term cancels out. We can then solve the divergence equation to absorb it into the new current, and then it really does have the right estimate. So somehow due to this special algebraic structure, special geometric structure, the terms that look most dangerous actually appear to be okay, and there are several such terms. And thanks to these cancellations, this whole proof goes through, and we get solutions where we cancel out the phi, kappa, and r at the same time, and in the end we get solutions that locally dissipate energy. So that's the entirety of my, that's all I planned on talking about. So I thank you for your attention.